Look at this blood. It's bright blue, flowing inside a living animal. It feels like it shouldn't exist, but it does, and it's worth up to $60,000 a gallon. Every year, hundreds of thousands of horseshoe crabs are pulled from the ocean, strapped to metal racks, and drained of that blue blood.
Most people have no idea this is happening, and yet our lives literally depend on it.
So why does this animal have blue blood? Who's buying it? And why are we willing to bleed an ancient species to get it? To answer that, you first have to understand what kind of creature we're talking about, because horseshoe crabs aren't what most people think they are.
Despite the name, horseshoe crabs aren't crabs. They're not crustaceans at all.
Genetically, they're closer to spiders and scorpions, ancient arachnid relatives that just happen to live in the ocean. And they've been doing it for an incomprehensibly long time. Horseshoe crabs appeared roughly 450 million years ago. To put that in perspective, fish had barely figured out how to have jaws, trees didn't exist. The entire land surface of Earth was barren rock. Since then, they've survived 5 mass extinction events that have reshaped life on this planet, including the one that killed the dinosaurs. They lived through the one before that, which wiped out 96% of all marine species. Not by adapting or evolving into something new, but by barely changing at all. They're so well adapted to their environment that evolution basically stopped trying to improve them. If you looked at a fossil from 300 million years ago and a living horseshoe crab today, you'd struggle to tell the difference. Same domed shell, same 10 legs, same book gills, same strange spike-like tail. They are, by almost any measure, one of the most successful animal designs in the history of life on Earth.
And the key to that success, the reason they've outlasted almost everything, is in their blood. Now, most animals you're familiar with,
mammals, birds, fish, carry oxygen through their blood using hemoglobin. Hemoglobin is iron-based, and iron, when it binds to oxygen, turns red. That's why your blood is red.
Horseshoe crabs use a completely different system. Their oxygen-carrying protein, hemocyanin, uses copper instead of iron. And when copper binds to oxygen, it turns blue.
But its color isn't the reason why it's so popular or expensive. The color isn't what caught the attention of the medical world. No, it actually has an unusual superpower. It's what the blood does when it encounters bacteria.
You see, when most immune systems detect a threat, they then slowly mount a response in the form of inflammation, white blood cells, and antibodies. But horseshoe crab blood doesn't do that.
It reacts instantly. If even a trace amount of bacterial toxin enters the bloodstream, specialized cells called amoebocytes don't just fight the infection, they explode. They rupture on contact and release a cascade of proteins that form a thick physical clot around the contamination. No inflammation, no immune escalation,
just an immediate self-sacrificing wall between the toxin and the rest of the body.
For 450 million years, this was just a horseshoe crab survival mechanism, an elegant solution to living in bacteria-rich ocean mud.
Then in 1956, a scientist in a small Massachusetts fishing village noticed something strange happening in his lab. And what he found would eventually make horseshoe crab blood the most expensive liquid on Earth and trap the species in a system it still can't escape.
It's 1950, and Frederick Bangs, a researcher, is doing his routine work at the Marine Biological Laboratory in Woods Hole, Massachusetts. It seemed like a normal day. Take the horseshoe crabs from his lab, inject bacteria into them for routine circulation research,
and watch how they'd react, as always.
But something unexpected happened. When certain bacteria entered the crab's bloodstream, the blood solidified everywhere. The entire circulatory system turned into a gel within minutes. Bangs realized the blood was responding to more than the bacteria themselves. The response was due to endotoxins, toxic molecules embedded in the outer membrane of gram-negative bacteria. These are among the most dangerous contaminants in medicine. They can cause fever, organ failure, and death in humans, and they're invisible.
You can sterilize a syringe, kill every living bacterium on it, and endotoxins can still remain on the surface.
Before Bangs' discovery, the standard test for endotoxin contamination was the rabbit test. You'd inject a sample into a live rabbit and wait to see if it developed a fever. It was slow, expensive, inconsistent, and required enormous amounts of animals. But now crab blood offered a new approach. Bangs, along with hematologist Jack Levin, spent the next decade refining what they found. By the late 1960s, they developed a way to extract the reactive component from horseshoe crab blood, a reagent they called limulus amoebocyte lysate, or LAL.
LAL could detect endotoxins in minutes with extraordinary sensitivity, down to parts per trillion. One test, one vial of reagent, and a clear binary result.
By 1977, the FDA began requiring LAL testing for all injectable drugs and medical devices. The rabbit test was phased out, and an entire industry was born, built on the blood of a single animal.
Every spring and summer, biomedical companies harvest horseshoe crabs along the Atlantic coast.
Primarily from Delaware Bay, the largest spawning ground in the world. The crabs are collected by hand or by trawl, loaded into trucks, and transported to sterile laboratories. There, they're washed, positioned on stainless steel racks, and a needle is inserted directly into the tissue around the heart, a region called the pericardium. Up to 30% of the animal's blood is drained over a period of 24 to 72 hours. The blood is processed into LAL, packaged, and sold to pharmaceutical companies worldwide. The crabs are then returned to the ocean.
But before I tell you what happens next, I want to talk about something a little different. Because keeping a documentary channel running takes more than just a camera and a good story. It takes a business, and businesses are complicated. That's where today's video sponsor, Odoo, comes in. Odoo is an all-in-one business management platform. And when I say all-in-one, I mean it. CRM, sales, inventory, accounting, manufacturing, project management, it's all there, fully integrated in a single place. And they built it to be flexible. Instead of forcing you to take everything, you pick only the apps you actually need. And any single app is free. If you want more, there's a free 14-day trial, no credit card required. For a small operation like mine, that flexibility matters. I'm not a Fortune 500 company, but I still want all the apps I use in one place. Odoo handles all of that with an interface that's genuinely easy to use and AI built into the tools that actually do the heavy lifting. The accounting alone has a 98% invoice recognition rate. You just validate, that's it. If you're running a business or building one, check it out at the link in the description. It's free to get started. Okay, back to the crabs, and here's where the story gets darker, because harvesting blood from horseshoe crabs isn't as clean as the industry makes it sound. Industry reported mortality rates sit at around 15%, meaning roughly 15 out of every 100 crabs die during or shortly after the bleeding process.
But independent studies have placed the real numbers significantly higher, between 20 and 30%. Some research suggests that even among crabs that survive, many are left disoriented, weakened, and less likely to be able to successfully spawn.
Imagine donating blood, except you can't have water for 2 days, you're handled roughly, transported in a truck, and then dumped somewhere unfamiliar. Even if you survived, you probably wouldn't feel great about it.
And the scale of the harvest is massive. In peak years, over 600,000 crabs were bled annually in the United States alone. That number has declined in recent years, not because of conservation success, but because there aren't enough crabs left to catch. And this is where the story expands beyond horseshoe crabs. Every May, horseshoe crabs crawl onto the beaches of Delaware Bay to spawn. A single female can lay 80,000 to 100,000 eggs in one season. Those eggs are tiny, energy-rich, and clustered just below the surface of the sand.
For millions of years, the spawning event has been the cornerstone of one of the most important migratory refueling stops on the planet.
The red knot, a small rust-colored shorebird, flies from the southern tip of South America to the Arctic every spring. One of the longest migrations of any animal on Earth. And roughly halfway through that journey, the birds stop at Delaware Bay, arriving emaciated and desperate. They depend almost entirely on horseshoe crab eggs to refuel. In the span of about 2 weeks, each bird nearly doubles its body weight, or it doesn't survive the rest of the trip. But as horseshoe crab populations have declined, so have the eggs. And with fewer eggs, fewer red knots make it through. Since the 1980s, the red knot population along the Atlantic flyway has dropped by more than 75%.
One animal's blood being drained in a factory is now quietly unraveling a migratory system that spans 2 hemispheres. But here's the part that makes this loss difficult to accept.
In the late 90s, a researcher at the National University of Singapore named Jikling Ding developed a synthetic alternative to LAL. It's called recombinant factor C, or RFC, a lab-made version of the same clotting protein found in horseshoe crab blood. It works, it's been validated in peer-reviewed studies, it's consistent, scalable, and it doesn't require a single animal.
And it's been available for over 20 years. So why is the industry still bleeding horseshoe crabs?
The answer is regulatory inertia. LAL has been the gold standard for so long that switching to RFC requires pharmaceutical companies to redo their testing processes.
A costly, time-consuming step that most have little incentive to take. The FDA has accepted RFC in principle, but hasn't mandated it.
The European Pharmacopoeia moved faster, approving RFC as a valid method in 2020, but in the US, where the majority of horseshoe crabs are harvested, LAL still dominates.
It's an economic problem more than a science problem, a tangle of regulatory caution, corporate inertia, and the simple reality that the existing supply chain, for now, still works, no matter the cost to the crabs.
In the words of one pharmaceutical testing executive, the industry has been, quote, glacially conservative, and the crabs keep bleeding. The horseshoe crab population along the Atlantic coast has declined so severely that in some areas, experts rate their recovery potential as 0. Not low, 0. An animal that has survived every mass extinction in Earth's history, every asteroid, every ice age, every volcanic catastrophe, is now being quietly bled toward collapse by the one species that figured out what its blood could do. The question now is whether we'll let these crabs keep doing what they've done for another 450 million years, or whether we'll be the extinction event that finally stops the clock.